Okay, so, oh, and you know what, even, I have PowerPoints for all this. Let's use the PowerPoints. I know, and I put these on the, somewhere on PowerSchool. Let me look real quick at where I put those. The PowerPoint that I'm going to use here. I'm pretty sure I put them on here last time. I can't put them in the content library because it's a PowerPoint and not like a PDF document. Where did I put it? Maybe in the resources? Or did I just put it in chapter 9? I must have just put it in chapter 9. Yeah. So if you go look at, if you look at the chapter 9 page in PowerSchool, the PowerPoints for the 3 lessons that we'll do in class are going to be there. So these are the PowerPoints that I'm using. So those are there for you. Oh, that's not what I want it to do. Nope. Yeah, this is all. Oh, this is what I'll do. This will fix it. This will be the easiest way to do it. Wow, I didn't know you were this intimate with him. If you aren't, then it seems like you're kind of being rude. I'm like, what? I said, I didn't understand. You mean Dave what? Oh, yeah. I guess that's why. You can't say John. You have to say John with that. My bad. There we go. Right. That was the easiest thing. Just unplug the extra monitor and then the computer knows where to put one. All right. Sorry about the delay, folks. So this, excuse me, the first section here that we'll talk about is just looking at calculating lengths inside of these 3D figures. As you might imagine, that'll be an important piece to being able to calculate a volume or surface area, is to be able to calculate the lengths of other pieces inside of a 3D figure. So the technique that we'll use to find those lengths is drawing something called a calculation triangle. So often, what we'll need to do is be able to draw some right triangle inside of or on top of our three-dimensional figure, and we'll call that triangle a calculation triangle. So for example, if we have the right pyramid drawn here, one possible calculation triangle that we might be interested in is this triangle CAB. So that's an example of a kind of calculation triangle. Now, this particular drawing has lots of possible calculation triangles that are not necessarily unique, right? Like there's several triangles that are identical to CAB here. In fact, there's 4 of them, right? one that's kind of where the point B is on, like the midpoint of each of the side lengths of the base there. But there's other calculation triangles inside of this, as you might imagine, right? There's one where B is at the corner of the triangle. That's a different calculation triangle. The side lengths will be different. Everybody's okay, get what I mean by where B's at the corner of the base? And then the other one would be where B and C remain the same place, but A would get moved to the corner of a base. And there's 8 of those that are all identical. So there's 3 different types of calculation triangle inside of this right pyramid. So if you can kind of imagine that in your mind's eye, that helps a little bit if you're able to kind of see that three-dimensionally and see where those different right triangles are, because oftentimes they don't all look like right triangles. You know what I mean? And you have to look at it with a little bit of perspective and some three-dimensional imagination, but that's what's going on. Okay? So that's just an example of what we mean by a calculation triangle. Again, we've talked about, so some of them, these right triangles can be a little bit hard to see because it doesn't necessarily look like they're right triangles. So if we take this cuboid, that's another name just for a cube, both the pink triangle here that's just in like the front face, easy to see that that's a right triangle. Everybody okay with that? This blue triangle though, where one side is the diagonal here, DG, the other side is this edge, FG, and the other is this interior diagonal, FD. That is also a right triangle, because I know that the sides of a cube, for example, the side GHCD is going to meet the side CGFB at a right angle, right? And that angle here, FGD, is the angle that those two sides are intersecting at, right? So that is a right angle there. It does not look it from the drawing. This is where like imagining it in 3 dimensions and kind of being able to unfold the figure a little bit is helpful. But they are both right triangles. They are different calculation triangles. The side lengths will be different. But they are both right triangles. And sometimes that's a little tough to see, especially in the beginning. Oftentimes in the problems, when, at least in the beginning, we'll be drawing the calculation triangle that you're interested in for you to help you get used to finding them. But this is really the most challenging part of this chapter, is just being able to find these calculation triangles. Or find the one that you need. Keep in mind that all triangles will not be right triangles, right? You can't just draw any triangle and have it be a right triangle. In a cuboid, you have a decent shot at that actually happening because you have lots of right angles in there, but it's not necessarily the case. Everybody okay so far? Again, we haven't really done anything yet. We've just kind of talked about this feature and made some observations about this feature. So again, some other unexpected ones. The pink one should be easy to see. That's just like half of this front side of our prism here. Should be easy to see that because it's half of a rectangle, should be a right triangle. The blue one, though, is also a right triangle. Again, because I know that the height of this triangular face should be meeting the top edge of our prism at a 90-degree angle. So this angle GBE is also a right angle, which makes this a right triangle. Again, once you kind of see that, it's a little bit easier to kind of unfold the thing in your head and look at it and be like, okay, if I were to look at this in 3 dimensions, I can see that it's a right triangle. Looking at the 2-dimensional projection of it onto a sheet of paper, it's a little bit harder to see. But once you know they're there, it makes it easier to look for them. That's kind of the point of what we're doing right now, is just to kind of show you some of these trickier ones to see. Just FYI, this term prism. A prism is a 3-dimensional figure that has 2 bases that are parallel, and then the sides of it are all rectangles. Those rectangles don't necessarily have to be the same size, but all the faces that attach to the 2 bases are all rectangles, which is what we have here. 2 triangle bases and then 3 rectangles that kind of connect them. And everybody's okay with that? We call it triangular because that's what the shape of the base is. If it was a rectangular prism, the bases would be rectangles, and then it'd be rectangles connecting it. You could have like a pentagonal prism, where you have pentagons and then rectangles connecting the 2 pentagons, etc. Everybody kind of get the idea there? So that's a piece of vocab that's maybe less familiar than cube. Anyways, those are 2 right triangles. Here's another example. This is another pyramid. It's a square pyramid, or at least a rectangular pyramid. I guess we don't know that it's a square pyramid because we're given no congruence marks on it. But it's at least rectangular. So we have 2 calculation triangles drawn in here. The one in blue is relatively easy to see. It's actually the same calculation triangle that we showed on the very first slide. And then there's this other calculation triangle, AFE, also a right triangle. The angle AFE is the right angle. And we know that the altitude of your pyramid should be intersecting the base of the pyramid at a right angle. So it doesn't matter where that other leg of your triangle is. If the one side is a altitude and the other side is in the plane of the base, it better, gosh darn, better be a right angle. Is everybody okay with that? And again, that one, if you think about it in your mind's eye, should be relatively easy to see. But again, you know, like taking that and getting it onto a sheet of paper with the right angle in the right place, with the labels in the right place, is not trivial in the beginning, right? It takes a little bit of creativity to kind of see that, but we're not doing anything we're not doing any calculation. I'm not doing any tricky thing. I'm not doing any complex procedure. I'm just kind of imagining what these things look like and using a little bit of common sense about what things really are at right angles. Is everybody okay with this? Am I beating this into the ground too hard? Do you get the idea? Okay. If it's confusing or you want to talk more about it, please stop me along the way, okay? Is it getting warmer in here yet? Okay. Okay. So let's do some examples here, okay? So let's say we have a shoebox that's 32 by 18 by 11, and then we want to calculate the length of the longest rod that'll fit inside the box. So let's think about our plan here. What would we want to do to kind of answer this kind of a question? Okay, so let's start by drawing a picture, though, right, of what this shoebox looks like. Everybody agree with that? And then we'd want to identify where that rod is going. So if you think about a box, what's the longest thing you can get? Good, so like the bottom corner to the top corner going on like a diagonal, right? Everybody kind of agree with that? So then we'd want to find, after we've done that, we'd want to find the calculation triangle that involves where one side of that calculation triangle is the rod. As Josh had pointed out, that's got to be a hypotenuse of some kind of triangle, right? Since it's the longest side of a triangle, it's certainly the longest thing you can fit in there is going to be a hypotenuse of something. And then we'll sketch and label and solve that triangle. So this is just kind of a little rundown of what we're going to kind of do. So I'll start by drawing ourselves a picture. So here's my 32 by 18 by 11 box. And so what Josh was describing is something, for example, going from F to D. Everybody agree that that's going to be the longest thing you could fit in there? And again, there's nothing specific about F to D. It could be from G to A or E to C or whatever, right? H to B. Okay? So I'm going to draw one in here. I drew G to A just because it was the easiest one to kind of draw with the way that I drew my box. It was the easiest orientation to put it at. Everybody's okay there? Okay. So there's that. Now, the problem with this is the only side of this triangle we know is GC. That's 11. We're looking for AG, but we don't know AC. If we knew AC, we could use the Pythagorean Theorem to find AG, but we don't know AC yet. Is it possible to find AC? Yeah. How would I do that? Yeah, there's a second calculation triangle we could use right here, ACD, and we use the Pythagorean Theorem there to calculate the length for AC. So when I do that, I get square root of 1348, whatever that number is. What, a little less than 40? Now that we have that, we can use the Pythagorean Theorem to find AG. So 36.7 is what it was. And that gives us 38.33. And again, as I'm doing these PowerPoints, if you need me to go back, that's fine. Let me know if I went too fast through something. But you also have access to these. These are all on PowerSchool, so if you want to go back and look at them, they're always there. Again, I appreciate that some of you guys are going to take notes no matter what. That's perfectly fine. I'm just letting you know that all the PowerPoints we're showing in this chapter are also on PowerSchool. Cool? Everybody feel okay about that one? And that's kind of a hard version of this 9.2 kind of problem, where we have two steps in order to kind of get to the answer we're looking for. Let's do another, yes? Yeah. Okay. So let's say that EABCD is a square-based right pyramid where the sides of the square are 12 centimeters and the height of the pyramid is 9.5 centimeters. We're first going to calculate the length of EC. And then after we do that, we're going to name some point M that's going to be the midpoint along one side of the base. We're going to calculate the length of EM. And then answer this question observing why EC is not the same as EM. So what should we do to start? Draw it. Yeah, we'd want a picture, right? So there's my square-based pyramid. So the sides of the pyramid are 12. I labeled the height of the pyramid as E. That's pretty typical in that the apex of your pyramid is usually the first letter, if you're given it listed as a 5-letter like that. So there's the height labeled at 9.5, and the sides are all 12. So the first thing we want to find is EC. Do we have enough information to find EC directly? No. So clearly I've drawn in a calculation triangle. What piece of the calculation triangle am I missing? FC, right? We're looking for EC. To find EC, we need FC first. Everybody good with that? Okay. So how can I calculate FC? Okay. So Josh says if I find AC, I can divide that in 2 to get FC. How do I know that that's actually half of the diagonal there? Because it's a right pyramid. So if that thing was tilted or something, like you had an Italian designer, that's me making fun of the Leaning Tower of Pisa, not Italians. It was not intentional design flaw. It had, the base was they built on a bad foundation. Anyways, if it was at an angle, that wouldn't necessarily be true. Now, we don't give you that situation in this course, but I just want to point that out to you. That yes, you're correct in this case that F does bisect that diagonal AB, or AC, excuse me. But that doesn't have to be the case. It's purely because this is a right pyramid. Okay, so we mentioned that. We're going to use triangle ADC. So there it is. So we can find AC really pretty easily. And then to get FC, we just divide that in half. So you guys seem like you're doing pretty good so far. Everybody feel the pace is okay? Again, there's nothing usually very tricky that we're doing. It's just sometimes it takes a little bit of time to get used to like finding things in 3 dimensions on a flat sheet of paper is sometimes not trivial. And again, like some of us will catch on really, really quick, and some of us it may take some time. Don't feel bad if it takes some time. It's nothing that you just got to give it time, right? Like you got to get some practice at seeing things in 3 dimensions. Some people are just good at that, and some people aren't. Ava, what's up? Okay. Okay. So now that we have FC and we know EF, we can find EC. And we get 12.74. Yes?
Could you have technically made it a smaller triangle if you went from F straight to the midpoint of DC and just did 6, both sides would be 6 then? And then you just kind of get the side from that instead of having to make a bigger triangle and then cut it in half?
Uh-huh.
Okay. That's
yeah. Or you could even have done this right triangle, where both of these are x and that's 12, and you could have done it that way also. Yeah, that's okay to do too. Sophia? Absolutely. Okay. On to part B. So again, it says that M is a midpoint mark halfway along one side of the base. So here's my M. We're going to now calculate the length of EM. So that's this piece here. So this is still 9.5. But FM is not anything we've covered so far, but it's not terribly difficult to reason out how long FM has to be. It has to be 6. Why 6? Well, since this is a square base and it's a right pyramid, F has to be at the exact center. So F is halfway along this side also. So this side has to be half of a side length, so 6. Everybody good with that? Okay. Easy to kind of miss that if you're not good at thinking about things in 3 dimensions, because it certainly doesn't look like it's, from a perspective standpoint, like half of a side length, right? And then we can just Pythagorean theorem that. And we get 11.4. Note that EM is shorter than EC, right? EC was 12 something. How do you know that that would have to be the case? That EC has to be longer than EM. You could have done this without even finding the 2 numbers first. You could have made that assumption. Well, consider the triangle MEC, right? That's a right triangle whose hypotenuse is EC, so it sure as heck better be longer than EM, right? Everybody, you guys agree with that? I mean, I get what you're saying, Cass. It's like, oh, they're all slanted, but I knew what you meant. Did you guys see that? And that's a great explanation as to why they cannot be the same length, right? Because they're both side lengths of a right triangle, and EC is the hypotenuse, so you know that it can't be the same length. Okay, let's do another. I think this might be the last example in the notes here for this section. So here's a cone, right? You do your best. So if the the slant edge of the cone is 11.3, and the angle at the apex is 53, we're asked to calculate the radius of the cone. Yes.
Awesome. Thank you.
Pull some strikes.
Okay.
Okay. Or try to anyways. Bowling's hard, you know? Well, harder for some people. It's hard for me.
Bowling is so hard.
Anyways, anybody with some ideas here? Yeah, so we're given an angle measure, so SOHCAHTOA is probably going to be useful for us. At least one of them, sine, cosine, or tangent. Everybody agree with that?
Yeah.
In particular, since we have a right triangle drawn in here, it's likely that we'll be using SOHCAHTOA and not like have to use the law of sines or cosines or something, since we have a right triangle clearly drawn in. Okay? So I claim that this angle is 26.5 here in my right triangle. How did I get that? Okay, how do I know that it's half? What is a midpoint? Okay, so D is the midpoint of... Well, D isn't part of the angle that we're bisecting. Okay, but how do you know that it cuts it in half?
It's a right cone. It's a cone.
Okay. Here's the better answer. The triangle ABC is what kind of a triangle?
Right triangle.
It is not right triangle.
It's a...
It's an isosceles triangle. Everybody agree with that?
Yeah.
So, we know that the altitude of an isosceles triangle bisects that angle. It also bisects this side, right? So the altitude is the same as like the perpendicular bisector. And it's also an angle bisector. This is a property of isosceles triangles. Now, I don't expect you to really remember that from geometry, as that's a pretty specific detail from a pretty long time ago. But I want to make a point that if you don't have a right cone, if that cone's tilted, that angle bisector goes right out the window. Becomes a much different problem. Everybody's okay with that? Again, we won't look at a situation like that in this class, but I wanted to point that out to you, that it's not an automatic. You do need that everything is straight up and down, which is handy for us since most of the building that we do is straight up and down, right? Nobody's interested in having a house on an angle. Anyways, so now that we've established why this is 26.5 and why it must be that, not just how we got it, but why we knew that was how we were going to get it. We can calculate R by using sine, so we can say sine 26 is equal to opposite over a hypotenuse, and then solve for R. Ooh, excuse me. And that's it for this section. What do you guys think? Well, do you want to do 2 sections today or 2 sections next time? Okay.
Let's procrastinate.
Procrastination wins.
That's fine. All right. You guys should be able to do... Oh, there's such good ones in here. You guys should be able to do 1 through 15. Nope. No, 1 through 15. There's only 33 or 32 problems in this section.
Is it section or chapter?
Oh, chapter. There's only like 32 questions in a review. There's no worksheet.
No, not like 150.
There's not 150.
Like last time.
Like last time, yeah.
That was funny.
So,
When I first started doing the homework for last chapter, and they were just like, so many more problems, I was like, this is gonna be a fun one.
you got your money's worth, that's for sure, right?
Definitely.
Yes, that's fine. Yeah, no problem.
Are these like types of graphs that you use? What? And then you only had 2, right? Yeah. Alright, thank you.
I don't need this anymore.
Yeah.